Hi everyone. Today we are going to start a very new and exciting topic of this probability chapter, which is conditional probability. So conditional probability is basically a type of probabilities where we say that if some event has occurred, then what is the probability of other event, right? For example, in this particular diagram, if I say, then this event, whatever it could be, like seems like it is tossing a coin. So if some tossing a coin has happened, then what is the probability of appearing, let's suppose 6 on this dice, something like that. So basically it is a change in belief, which means the probability of any event based on some partial information. Like let me just give you the example. Suppose that India and Australia are playing, and if you don't know anything, you don't have any prior information that which team is stronger today or which team is performing well nowadays, or any other information or any other prior belief that you, let's suppose, you don't have, then in that case, if I just ask you that what is the chance of India winning, then what will you say? Just think about it. Since you don't know anything about the India, you don't know anything about the Australia, then you will say the chances are equal, right? Why you will be biased? I mean, you will be biased only if you know some information. But I'm saying that let's suppose that conditions are very fair, all teams are equally good. In that case, you will say that okay, this is 0.5, which is the probability where you are saying that chance of India or chance of Australia winning is 0.5 probability. But on top of that, if I give you some more information, suppose if I say that India scores 395 and India is batting first. India has bat first and India has scored 395. Then what is the chance of India winning? Now, since I give you some information, then you might infer something, right? From this, you will say that okay, now, since India has scored quite high, probably India will be winning, right? Which means you will say that okay, the chances of India winning is greater than 0.5. So what is happening here is that you earlier did not know anything. You said okay, the chances are equal, but now you know some information, and the information is that India has already scored 395 score, and now with this information you are changing your belief, which means you are saying that okay, now there is higher chances that India will win. So this is all about conditional probability. Conditional probability is basically change in the belief. Whatever you already know, it might get changed if there is some other information that is given to you, right? Let me give you more examples. Probably after that it will be more clear. So okay, continuing on the same example first. So suppose A is an event where I will say India is winning, and B is an event I say that India scores 395 runs. And if I just ask you probability of A, then you will say it is, let's suppose, 0.5, that India is winning 0.5. But if I just say, like, just notice this notation, this slash B means given the B, it is read as probability of A given B, which means given B means here B is India scores 395. So it means that if given that India has already scored 395, then what is the probability that India is winning? In this case, you will say that okay, this is greater than 0.5, right? I hope you understood. So basically, these two are not same. That's what I wanted to convey. That if you know some belief, then probably your, if you know some information, then probably your beliefs are changing. And also note that there is no relation between these two, which means that if I just say probability of A given B and probability of A, if you just ask me that which one is greater, maybe in this case this is 0.5 and this is greater than 0.5, so maybe in this case it is greater. But let's suppose the event B is that India has scored, let's suppose, only 50 runs. Okay, event B is India has scored 50 runs. In that case, you will say that since India has scored 50 runs, there is very less likely that India will win. So that's why it may be 0.1 or something, right? In that case, you will say that okay, probability of A itself is greater. So basically what I'm saying here is that there is no relation between these two, which means maybe this is greater, maybe this is greater, maybe both are equal, right? So there is no relation at all. No relation between probability of A and probability of A given B. No relation means no relation in terms of which one is greater, which one is lesser. Okay, cool. Now I hope that is understood to everyone, that like your beliefs are changing. Now let's just move to some other example, and probably by the end of this lecture it will be completely clear that what do I mean by conditional probability. So this is just introduction to conditional probability. Let's just be with me. Okay, I mean you just be with me and just try to solve any of your doubt you are having in this lecture itself. Okay, so just consider this example where we are saying that we are throwing two dice. Now in these two dice throw, I am saying that what is the probability that sum of two faces is 9. Okay, let's just calculate what is the probability the sum of two faces is 9. There are total 36 possibilities are there, isn't it? And sum of two faces is 9 means I think let's see. I think with 2 it is not possible to get 9 because other has to be 7. So maybe let me start with 3. So with 3 6, yeah. With 4 it will be 5. With 5 it will be 4. With 6 it will be 3, right? I think these are the 4 possibilities out of 36. Out of 36, these are the only 4 possibilities where the sum of the faces is 9. So the probability that sum of two faces is 9 is 4 by 36, and eventually it will be 1 by 9. Because these are the only possibilities here. So what you are saying here is that if someone asks you the sum of the face is 9, sum of two faces is 9, you will say the probability is 1 by 9. Okay. Now let me just put some extra information to this. Suppose my extra information is looking like this. Suppose I say that I ask you the same thing, but I say something else, which means suppose I say that you already know one of the face is 6. Okay, you already know that first face is 6. Let's suppose. Okay, given that, let me write it as B. We know first face is 6, right? In that case, what is the probability? See. Now let's just see. You already know that first face is 6, which means that this is the only possible outcome that I am talking about. Okay. See, let me do one thing. That here, let me just go step by step. Here, first I am asking that what is the probability of two faces, sum of the two faces is 9. You said it is 4 by 36. Now I say that okay, I already know that first face is 6, which means that if first face is 6, then the second face could be 1, then 6 2. Then 6 3, then 6 4, then 6 5, and then 6 6, right? I already know that first face is 6. Then what is the probability? The sum is 9, which means that out of these, how many are having sum 9? I think 1, right? I think 1. So this is 1 2 3 4 5 6. Yeah, out of 6 possibilities, only 1 is having 9. So now it is 1 by 6. Why? Because I already know first is 6, which means I reduced my sample space. So I will talk about it later, but like I don't want to go into the technical details as of now. But yeah, just listen here. What I'm saying is that we are reducing our sample space based on some prior knowledge, right? So the knowledge here is that you already know that first face is 6, which means your sample space is not the random sample space or not the exhaustive or the complete sample space that we started with. Now the sample space itself has been reduced, which is saying that okay, you consider only the events, only the pairs which are having 6 in the starting. Now if you consider only these pairs, and now if you ask me the probability that sum is 9, I will say that out of these 6, everyone is equally likely. So 1 by 6 is the probability of 9. Yeah, as of now it might be little confusing, but don't worry, it will be clear with more examples. Okay. So see here that if I just ask you that okay, first phase is 4. Here I'm giving you first phase is 4. Then in that case, these are the only possible results, and among them 4 5 is only giving 9. So 1 by 6 is the probability. If it is given that first phase is 4 or first phase is 6, right? So what is happening here is that earlier your probability was 1 by 9, but since you now know the different information, I mean, you already know some information. Based on that, probability may increase, may decrease. Like as I said, like there is no particular relation. It may increase, it may decrease, right? So, but it is changing, or it may also not change. I mean, it may also not change. It is not compulsory that it will change. I will show you the example. Okay, so it may also not change. So, but yeah, in this case, the 1 by 6 is the correct answer. So let me just give you some naive example, maybe. Okay, maybe I can give you some naive example also. Suppose. Let me take one example. Suppose if I say that 1% of the people in this whole country are having COVID. Okay. So suppose I say that 1% of population has COVID, which means that out of 100, 1% means 1 by 100, right? Which means out of 100, 1 people or 1 person is having COVID. Now there are many persons in this country. So now if I just ask you what is the probability that someone is having COVID, you just randomly pick a person. Okay, you just pick me, and then if someone asks you what is the probability that I am having COVID, or randomly pick anyone. Okay, so someone is having COVID. What is the probability? What do you think that someone is having COVID? Since out of 100, just 1 person is having COVID, or 1% of the whole population is having COVID. So let's suppose the whole population could be 1 million or whatever, like let's not worry about it, but whatever it is, out of, like, you will say that x number of people are there, then x upon 100 people are basically having the COVID, right? So out of 100, just let's assume that there are 100 people only. Okay, let's assume, like for example, for the sake of simplicity, let's assume there are 100 people only. Then if you randomly pick someone, what is the probability that person is having COVID? Since only one people is having COVID there, because out of 100 only one is having COVID, if you randomly pick someone, then maybe you are picking that particular person, right? So basically here the probability is 1 by 100. Why? Because you are picking someone randomly, and then random person could be the COVID infected person itself, because there are only one person which is having COVID out of 100. So let's suppose there are 100 people in this country, and out of 100 only one people is having COVID. You randomly pick someone. What is the probability it is having COVID? Maybe 1 by 100, right? But now if I give you more information, okay, if I say that probability that particular person, okay, I mean, you picked someone, okay, you found out that the person is basically having some symptoms of COVID, okay, you picked someone, see, the sequence is like that. You first pick someone, and then you found out that, okay, that person is having COVID, person is having symptoms of COVID. I mean, that's not verified with the lab, but yeah, with the, visual symptoms, you can say that, okay, that person is getting symptoms of COVID. So I say that you pick someone, and then you found out that person is basically having like having symptoms of COVID, having symptoms of COVID. In that case, if I ask you, what is the probability that person is having actually COVID, then you will say most probably like 1, like most probably if it is having the symptoms of COVID, then most probably the chances are that the person is actually having COVID is, let's suppose, almost equal to 1. Basically your beliefs are changing, right? Earlier it was some random belief, but now you know something, and then you are saying that, okay, what is the probability the person is having COVID? Now your beliefs are changing. Anyway, like, this is not any mathematical example, but just one intuitive example I wanted to give you, just to let you know that, okay, the beliefs are changing based on some other information that you already know, right? Cool. Okay. Now let's just do this question. What they're saying, a die has been rolled where the additional information is given that the experiment has produced an even phase. What is the probability that 2 has occurred? See, you are rolling a die, and now they are saying you that whatever has been produced on this die, like, now whatever was the front face of this die was an even number. What is the probability it was 2? See, let's suppose that nothing is given to you, okay, nothing is given to you, which means a die has been rolled. I say just a die has been rolled, and what is the probability that it is 2? You get 2. You will say that, okay, 2 by 6 probability, because there are six faces. Okay, sorry, 1 by 6 probability, because there are 6 faces, and then you are just talking about only one of them, right? So 1 by 6 probability. 1 by 6 probability, I can say occurring 2, right? Occurring 2 on the dice. But now they have given some additional information, and what is that information? They are saying that the additional information is that experiment has been produced and you have found the even phase, which means now just list out all the even phases, 2, 4, 6. Now they have given that you don't need to worry about 1, 3, 5, these kind of outcomes. They are already giving you the hint that, okay, see, it was either 2 or 4 or 6. What is the probability it was 2? You will say, now given this information, you will say it is probability occurring 2. Given that you already got even phase, now given this information, it is 1 by, because everything is equally likely, it is 1 by 3, right? See, let me just tell you what is happening here. That earlier, let's suppose there are 6 outcomes are possible, okay? Let me just list down 6 outcomes: S1, S2, S3, S4, S5, and X6. And I'm saying earlier, everyone is equally probable. This is 1 by 6 probability. 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 This is also 1 by 6 probability, and this is also 1 by 6 probability, right? Cool. Now I'm giving you one additional information where I'm saying that 1 has not occurred, 3 has not occurred, 5 has not occurred, which means I'm clearly giving you the hint that clearly says that the probability that 1 has occurred is actually 0. The probability that 3 has occurred is actually 0. The probability that 5 has occurred is actually 0. Which means these 3 probabilities are 0. Now you are just asking that what is the probability of this? What is the probability of this? This is the question, right? So I hope you are getting the question. So what we are doing, this is the initial sample space. Now they are actually telling you that you can reduce your sample space and work now, which means that this 135 has never occurred. And now according to that, you have to work on the problem, right? Now here, since these are never occurred, I will say the probabilities are 0. Now, do you think that these probabilities are still 1 by 6, 1 by 6, 1 by 6? Do you think these probabilities are still 1 by 6? If these probabilities are 0, you have to somehow balance the probability mass, because the total probability mass has to be 1. If you sum all these discrete probabilities, then ultimately it should be 1. So there should be some change in this 1 by 6, right? You cannot keep these 1 by 6 as it is. I hope you are getting the reason. So see, slowly we are building the foundation of conditional probability. So I want you to think about it. See what I'm doing, I'm just shifting the probability mass from this 1 by 6, I'm making it 0, I'm making it 0, I'm making it 0. Which means I'm redistributing my probability masses, right? Which means earlier it was, if it is 1 by 6, now it cannot be 1 by 6 anymore. Reason is very simple. What is that reason? Reason is that if we sum these 3, it should be 1. Like ultimately everything should be 1, right? But now it is not 1. It is, I think, a 3 by 6, which is like 1 by 2, right? Which is 1 by 2. It is actually not 1. So what can we do to make it 1? I hope the problem statement is clear to everyone. So what we are doing, we are first reducing the sample space. Now on the new sample space, we want to redistribute the probabilities, right? So let me just give you the hint that how we can redistribute these probabilities, and then finally we can eventually derive the conditional probability formula. Okay. So let's just redistribute these probabilities. See, one thing is very much clear, that these cannot be 1 by 6. We need to redistribute these probabilities such that ultimately the summation is 1, right? So let's just do one thing. Let me write the 1 by 6 here, this 1 by 6 here, this 1 by 6 here. I want this summation to be 1. So ultimately I want this to be 1. Currently it is 3 by 6, which is actually 1 by 2. Now if I want that to be 1, okay, the summation to be 1, what do you think I can divide? Okay, which number I can divide such that the ultimate summation is 1? See, if it is 1 by 2 on the right hand side, okay, let me just remove this 3 by 6 probably, okay, just to give you the better visualization. So let me remove this 3 by 6 here. So this is actually 1 by 2, right? Now what I want the summation to be 1. Cannot I divide by 1 by 2 both sides such that the summation is 1? Then it is basically, if you are dividing 1 by 2, it is basically you are multiplying by 2 or whatever, right? So basically it will be 1 by 6 into 2, right? 2 into 1 by 6 plus 2 into 1 by 6 plus 2 into 1 by 6, which is 2 by 6. So basically what is happening here, you want to redistribute the probability, and now it is 1 by 3 plus 1 by 3 plus 1 by 3, now it is 1, right? So instead of 1 by 6, now the new probabilities are, can you just tell me now? 2 into 1 by 6, which is 1 by 3. See, this 1 by 6 is actually wrong. Reason being is that this is not giving you the summation of 1. So we wanted to redistribute the probabilities in the same proportion. Like I will talk about the proportion a little later, but yeah, in the same proportion. I will tell you that what do I mean by the proportion. But yeah, it is now currently 1 by 3. It is 1 by 3. It is 1 by 3. It cannot be 1 by 6. So maybe I can just remove this 1 by 6, right? It cannot be 1 by 6. It has to be redistributed. And that's the beauty about this conditional probability. So let me just write here, this has been redistributed, right? So this is redistribution of the probability. Distribution, right? That's very, very nice and intuitive understanding of conditional probability, that you get the new sample space based on the prior information that you know, and on that sample space you are actually redistributing the probability. Now if someone asks you that what is the probability of being 2 given that, okay, you already got even phase, then you will say that it is 1 by 3. Earlier also, if you remember, we got the 1 by 3 answer, right? I have actually listed down all the things, and then I got 1 by 3. But yeah, I will tell you the formula, and this is the way to go to formula, which means this is where we are actually building up the intuition, so that finally we eventually land up to the formula, right? Now like once you know the formula, you don't need to do all of this. It is just a, as I said, like it is a way to formula. So currently we are just building the intuition to get the formula. See, in this current scenario, I have not listed down all of this 2, 4, 6 or something, right? I have not listed down 2, 4, 6 or something. Still, I got the answer 1 by 3 using the redistribution of the probability, and that's where the formula comes into the picture. Okay, I will tell you the formula. Don't worry. So what we are saying is that we want to redistribute the probability. Okay. See, it is a new sample space. Basically, what we just got is a new sample space. Actually, this is not required for gate, so I might not do it in very much detail, but yeah, let me just tell you one thing, which is about the new sample space. See, earlier your sample space, okay, the old sample space was like this, and this is new sample space. So earlier the old sample space was having 1, 2, 3, 4, 5, 6, and now here I am saying the probability of, let's suppose, 2 was 1 by 6, right? Now the new sample space, let me define it by maybe omega prime, that is just getting 2, 4, 6. And now here the probability of 2, okay, since the probability is a function, I can use q here. I mean, that's perfectly fine. You use p here because in the sample space I'm defining the p as a probability, but here let me just use q so such that it doesn't get mixed up. Okay, so q means probability, like probability in this particular sample space, okay, of occurring 2. What is the probability of occurring 2 in this new sample space is, let's suppose, q. Okay, then q of 2, then it is 1 by 3. See, the probability is a function. You represent it as a p, you represent it as a q, does not matter. But yes, in most of the cases, and in fact all the cases, we will be representing it as by p. But there is no harm in representing by q because I don't want to mix up the notations, right? Okay, yeah. So now, interestingly, if you want to do this 1 by 6 here itself, okay, which means in the old sample space here itself, if you want to do 1 by 6, then what you can do, you can basically write something like this, which is where the conditional probability comes into the picture, that probability of 2 given that even phase, and then you can write 1 by 3. You cannot write directly, you cannot write probability of 2 is 1 by 3. Okay, you have to write given that. If you directly want to write, you have to go to the new sample space and you have to talk about q. You cannot work with the p anymore now. So by the way, like these things are not at all required for gate. So that's why I will just give you a glimpse and then I'm skipping it. Reason is very simple. Like we don't want to entangle ourselves in the technical details. We just want to get the intuition. We just want to cover all the things which are required for gate, even required for the interviews. But don't don't get into the entanglement of all of this, right? So let's just skip this all of this technical jargon, and I will directly tell you the intuition with one more example. So here I will say that not required for gate, right? Not required for gate. Cool. I hope you understood. Now let me just give you one more example. Okay, let's just say that you have some sample space which is S1, S2, S3, S4, S5, S6. Okay, these are the, let's suppose, 6 outcomes here. Now suppose this is having 1 by 2 probability. Maybe this is having 1 by 8 probability. Maybe this is having 1 by 4 probability. I mean, I'm having a different probabilities for everything, so that I can give you some different example. Okay, this is 1 by 4. This is 1 by 4, which is okay. I think already I did it 1 by 2, right? This is 2 by 8, which is 1 by 4. Then 1 by 4 plus 1 by 4, it is again 1 by 2. Okay, so maybe I can say that, let's suppose, these are the only 4 outcomes. Okay, or maybe let me do one thing. Maybe let me just make this as 1 by 8, or maybe this is 1 by 4, and then what is the remaining here? Remaining here is, this is 1 by 4, 1 by 4 plus, okay, 1 by 4, 1 by 4, 3 by 4, right? And I think 1 by 4 is remaining. Okay, if 1 by 4 is remaining, let me just do 1 by 8, 1 by 8. Okay, I hope that's fine. Yeah, so the summation of all the probabilities should be 1. Let's just check it. 1, 2, 3, 4. So 4 by 8, which is 1 by 2, 1 by 2. Yeah, so this is 1. Cool. Now let's suppose these are the initial probability distribution that you have. And now what you want to do, let's suppose someone just said that, suppose that that S2 and S3 maybe, let's suppose they say maybe that S2, S5 has not occurred, or maybe they say that S1, S3 or S5 has occurred, or something like that. They say that, okay, that S1, S3 and maybe S1, S3 and let's suppose S5 has occurred, and S2, 4 and 6 has not occurred, which means they just give you the additional information that these probabilities are 0. And now you are asked to find out these probabilities, the new probabilities in the new sample space or something like that, right? Now can you do it using the redistribution of the probability? Just think about it, that how you can redistribute the probability and still get the nice and same answer. I mean, still get the final answer, which is the correct answer. See, let's just do step by step. Can you write 1 by 4 here? Can you just say it is just 1 by 4, 1 by 4, 1 by 8? Obviously no. What is the reason? Because the summation is itself, this is the 1 by 2 plus 1 by 8. What is the summation here? 1 by 2 plus 1 by 8. So I think this is 4 by 8, 5 by 8, right? The summation is 5 by 8. Now you will say the summation is not 1, right? Summation is not 1. That's the problem here. So because the summation is not 1, you can't say this is 1 by 4, 1 by 4, 1 by 8. You have to redistribute them. Okay. So now let's just try redistributing them. Let's just see if we can actually do it. It will be a nice exercise if you can do it. Like just pause this video and just try doing it. Okay. So see here. Now if we just find out the summation, which is 1 by 4 plus 1 by 4 plus 1 by 8, then it is coming out to be 5 by 8. Now if I just ask you that with what number you can divide on both of the sides such that you get 1 as an answer, right? This is called redistribution, or some people call it normalization. Normalization means making everything as 1. Okay, normalizing the things. Okay, I mean, like these are just again technical details, like you don't need to worry about this normalization and all. But yeah, in machine learning actually, like people say it normalization, so I just throw on some machine learning term that you don't need to take it. Okay, so yeah, let's just say redistribution of the probability. So now I'm redistributing the probabilities and I'm saying let's just divide by 5 by 8, which means this probability is now 1 by 4 into 8 by 5, right? Or 1 by 4 divided by 5 by 8. So this is not anymore 1 by 4. It is 1 by 4 into 8 by 5. Similarly, this is also 1 by 4 into 8 by 5. This is also 1 by 4 into 8 by 5. And this is also 1 by 8 into 8 by 5. So now, if you just calculate the final probabilities, you will be getting 2 by 5. This is again 2 by 5. This is again 1 by 5, right? Now you will say that probability that S1 has occurred, given that S2. Okay, so if someone asks you that what is the probability, now you know the answer, right? If someone asks you what is the probability that S1 has occurred, given that S2, or maybe I can say S1, S3 or S5 has occurred, given that S1, S3 and S5 has occurred, which means someone told you that okay, these, like I am giving you the hint that these 3 has occurred, then what is the probability that out of these 3 S1 has occurred? Then you will say that 2 by 5 is the probability. Now similarly, if someone asks you that what is the probability that S2 has occurred, given that S1, S3, S5 has occurred, then just tell me. Then you will say 0, right? You just told me that S1, S3, S5 has occurred, and you are just asking me that what is the probability that S2 has occurred. Obviously 0, right? So I hope you understood that how does this redistribution of the probability is working. That's very, very nice concept. I hope you get it. Even if you don't get it, that's perfectly fine, because we have the formula with us. Okay, but yeah, currently we are just building upon the basics. Cool. Let me do one thing. Let me just show you the formula, and then we will come back to this intuition. Okay, so let me just show you the formula. See here, this is the formula of conditional probability, where I am saying the probability of B has occurred, given that probability that of A has occurred, given that B has already occurred, is this formula, right? So let's just try understanding this formula and why we are dividing and all. Let's just try understanding this. So what this formula is saying, that probability of A has occurred, probability of A will occur given that B has already occurred, is this one. Maybe at first sight it is counterintuitive. I mean, it is not coming natural to you, right? To be honest, there is no proof of it. I mean, we can't prove it because that's the definition of conditional probability. That's how it is defined. Okay, so there is no particular proof of it. Still, we will just try to understand this using the intuition. Is this clear? Now let's just give some example. Let me just give you some example. Let me just give you more intuition behind this formula. Although again I am saying that there is no proof of this formula, because this is by definition conditional probability is defined like this. Still, if we can do with the intuition, then why not, right? So let me just try building some intuition. Suppose there is a sample space. In that sample space, you have maybe 15 outcomes are possible. Let me just list down all the 15 outcomes. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So these are the 15 outcomes that we have. Now here, if I just ask you that what is the probability of A given that B has occurred? Okay. Before that, let me just mark A and B. Maybe I can say this is A. Okay. A is basically consisting all the all of these 6 events. Let's suppose all of these 6 outcomes. So I said this is A. Okay, this is A, and let me also mark B somewhere. Maybe I will say this is B. This is B. And if someone is asking you, let's suppose every outcome is equally probable. If someone is asking you that what is the probability that B has occurred, A has occurred given that B has already occurred. Okay, so this is the question. See, earlier in this particular diagram, I will say that everything is equally probable since there are 15 outcomes. So 1 by 15, 1 by 15, 1 by 15. Okay, this is actually initial setup. Now they have given you additional information, which is that B has already occurred. Right? This is the additional information that they have given you. So using this information, what you can do? Just think about it. You will say if B has already occurred, then let's just redraw this diagram, because now everything other than B is not possible, right? So let's just redraw this diagram, and let me just say that everything other than B is actually not possible, which means I can actually just say that these events are not possible at all, or maybe I can even I can even delete it, but yeah, that's fine. So I'm saying that these events are not at all possible. Cool. So I hope you understood. Now only events in the B is possible. See, earlier everything was equally probable, which means everything I was saying 1 by 5, 1 by 15, 1 by 15, 1 by 15. But now looking at this also, everything is equally probable. I mean, that's not an issue. Like whatever the proportion, see, I will talk about this proportion later. But yeah, you can understand intuitively that whatever the proportion earlier was each of this was everything was equally probable. Here also everything is equally probable, right? I mean, this is the diagram that I say B has already occurred. B has already occurred. Now, since earlier was whatever the proportion earlier was, here also the proportion will be same. Earlier I was saying everything is equally probable. Now also everything is equally probable. But can it be 1 by 15? That's my question, right? Can it be 1 by 15? If everything is equally probable in this four elements, then it has to be 1 by 4, right? It has to be 1 by 4. But I mean, intuitively you might understand that from 1 by 15 we are going to 1 by 4. But how we are going using the formula, or how we are going using the redistribution of the probability, that's what we need to understand here, right? So you can say that yes, earlier here everything was 1 by 15, 1 by 15, 1 by 15 like that, right? Everything was 1 by 15 here. Earlier, this is the story before B has already occurred. But now story has changed. Now B has already occurred, and now in this case, I will say then you have to redistribute the probabilities, because some of the probability mass is shifting here and there. See here, the probability of this particular sample space, or this particular not the sample space, this particular outcome is actually 0, right? The probability of this particular outcome is actually 0. So these probabilities are 0. Earlier these probabilities are 1 by 15. So the probability mass is shifting here and there. Now let's just see if we can redistribute the probabilities and still we can get the answer. Isn't it is a nice exercise to do? Do you want to do it? Just pause this video. Let me know that what is the answer you are getting here. Okay. So okay, let's just do one thing. Let's just continue this in the next video, where you just have to comment out that after redistributing the probability, what you are getting here. Okay, 1 by 15 is actually wrong, right? This is actually wrong. You need to tell me the correct answer for all of these events. Do it using the redistribution of the probability. Okay, so let's meet in the next video.